Hi everyone, I'm Susan Lowell de Solorzano, and I'm coming to you from Washington, D.C. in the United States of America. I'm here to present a systems view of biology, biotensegrity, and its fractals and spirals. For those of you who don't know me, I am a student and teacher of Tai Chi Chuan, otherwise known as Tai Chi. In 2012, I co-founded DC BIG, the Washington, D.C. area biotensegrity interest group. I'm an associate of Steve Levin, Dr. Stephen M. Levin, who came up with the concept of biotensegrity back in the 70s. And in 2015, Steve and I, along with his wife Olga, founded the Stephen M. Levin Biotensegrity Archive. Also in 2015, we hosted the European Biotensegrity Interest Group for their Big 7 meeting, and we organized the Biotensegrity Summit. And then with COVID, I became a co-producer with Graham Scarr, Chris Marita Clancy. The three of us worked together on the Biotensegrity Party, which you can see on YouTube. And then in October of last year, my book From Handspring that I've been working on for about almost 5 years was published. It's called Everything Moves, How Biotensegrity Informs Human Movement. It has a foreword by Steve and an essay called Bone is Fascia, also by Steve Levin, that Graham and I contributed to. 10 wonderful movement teachers contributed essays to the book. The book includes about 100 experiential activities, so you can learn biotensegrity by feeling things and doing things. And it was sort of designed to be a beginner's textbook to biotensegrity and to show the state of the field at the time of the writing. Here's an overview of what I'm going to be presenting on today. I'm going to be talking about 2 quests, both mine and how I came to biotensegrity, and Steve's and how he came to originate the concept many years ago. Then we're going to talk about functional structure, both in materials and in living organisms. We're going to talk about biotensegrity and what it is and why it matters. And I'm sure most of you know that biotensegrity applies from viruses to vertebrates. So we're studying a whole system for biology. And then we'll look at the distinctions between tensegrity and biotensegrity and the many wonderful inventions and applications and inspirational ventures that people go on when they are inspired by and informed by biotensegrity. And those would be separate from biotensegrity itself. And then finally, we'll look at biotensegrity as a systems view of the spiraling, fractal functional structures and behaviors of living organisms. So on to our 2 quests. We'll look at Steve's quest first. He went to the Bronx High School in Science, grew up in New York City, and trained to become an orthopedic surgeon. During that time, he also trained in manual medicine with John Monell and learned his techniques for resolving problems in the body. Because Steve was conventionally trained in medical school, he learned traditional biomechanics, which include the perspective of looking at the spine as a column and modeling the body as a machine, as if it could be assembled from parts, and then coming up with numerical calculations which make the assumption that the same calculations we can use when we measure things with machinery could apply inside of our human bodies. Now, this was a problem for Steve because he knew, working on bodies, that bodies don't behave like buildings and machines. So he was, for a long time, looking for a different model that would explain our cohesiveness that's independent of gravity, for example, that would explain our material and energy efficiency, and that would explain how we are holistic, integrated organisms. In pursuit of trying to solve his problem, he went to the National Mall in Washington, D.C. here, and it's not a shopping mall. It's a huge expanse of many acres that includes the Capitol, the Washington Monument, the Lincoln Memorial, many of the Smithsonian museums. Steve went there specifically to go to the Natural History Museum because he thought maybe in trying to figure out the problem of living structure, he could get clues by looking at the bones of the largest organisms that ever lived. So that's Steve's journey, and we'll talk a little about my quest. I was studying Tai Chi Chuan, and my unsolved problem came primarily from my study of the Tai Chi classics. These are the ancient writings that are given to us when we study Tai Chi, and a lot of these words were very enigmatic or confusing or seemed mystical to me. Yin does not separate from yang, yang does not separate from yin, yin and yang complete each other. We're definitely in this way studying a system, and Taoism and the Tao Te Ching are things we also study, and we're studying the world as a system. Also in the classics it says, yin and yang should be differentiated clearly. Each part of your body is either yin or yang, and every point always has both yin and yang. So that's telling us that there's some complexity here, and actually that it's a fractal system. We're supposed to be regarding this Taiji symbol, which in the US is called the yin and yang symbol. Those little dots, we're supposed to be imagining those as having another yin and yang symbol inside each of those two dots. Those symbols, of course, having their own dots with more symbols inside. So that is a fractal system that we are learning about. We also learn in Taiji that the body is one unit and should be regarded that way, with all of the parts threaded together. So we're looking at a body system that is integrated. When one thing moves, everything moves. When one thing stops, everything stops. So there's a global responsivity that's perhaps being conveyed there. Just a few more of these. In the Taiji classics it says, seek the straight in the curve. And for me that was a very confusing one. Talking about spirals emerging out of straight lines is something we'll be getting to later today. And so those are emergent properties that come as part of the system. Though the transformations have a myriad of varieties, They are of one nature. So out of one movement system come an infinite number of possibilities. And that is indicating that things about the body are incalculable. If he doesn't move, I don't move. If he moves, I move first. Only by practicing for a long time can one suddenly understand it. These indicate non-linearity in the process of learning and in the process of practice. So that's what was sort of motivating me when I was looking around for something that would help to explain these mysteries. So those are the two quests. Let's move on to functional structure. And we're just going to talk about a few basic points here. We're going to talk about push and pull, and forces, and triangles, and how things fall together, and what living things need in terms of functional structure, and the structural options that living things have, and tensegrity. So if you would, right now, try some of this with your hands. Push them together, interlock your fingers, and pull, and just keep experiencing push and pull, and notice, what do you feel where? Understand that a force is an interaction, and your hands are interacting to create these push and pull forces. Now, when you're looking here, can you sense, where is the push? Where is the pull? And what about here? Knowing that forces are interactions, can you sense the pull of gravity? Can you sense the push of one block upon another? The Washington Monument, like just about everything you've ever seen, is a continuous compression structure. One block is built upon another, and the push and pull forces within are lined up. So everything works out well. But what happens if you're building something and those forces are not aligned? You've all seen this before. You can almost feel the problem. The problem is called shear. Shear happens when push and pull are acting simultaneously within a given structural unit. The two forces are working at cross purposes. It puts strain on the materials, which reduces the material efficiency. It reduces the energy efficiency. And the structure starts to tear itself apart from the inside unless something is done to resolve the problem. Now, both of these are gravity-dependent structures, which for thousands of years is how humans have been building things. They're called continuous compression structures, and the question becomes, when you're building anything, how do you prevent this shear? If you line everything up, you won't have a problem. But that Washington Monument on the left, those blocks are much thicker at the bottom than at the top, because internally they're trying to avoid buckling. Humans figured out at some point that if they triangulated things, they could reduce shear in the system, because triangles can separate those push and pull forces so that they can be distributed by different elements in the system, and so that the forces are not working at cross purposes. So triangulated structures can reduce shear. because a square frame, if pressed, if forces come to bear, it's going to collapse unless you use a lot of material and energy to reinforce those corners. But a triangle is naturally stable. It's an efficient system because the component parts work together, and then it functions as a one. And on the left, you'll see a version of a tetrahedron, and we'll look at those a little bit more in a minute. But the point is that engineers have long known that triangles can function as systems and can be interlinked to create functional systems where forces can be distributed. So triangles are systems. They distribute the forces effectively. They're materially efficient. They're energy efficient. And the push and the pull forces are separated among the different constituent parts of a multi-triangulated structure. So the forces are not working at cross purposes, which means there's no shear effectively. And so for this reason, we study triangles a lot, and we study how things naturally fall together. And spheres will close pack into triangles, as you see here. And those triangles will naturally form hexagons. And so you end up with systems within systems within systems. And it's a much more complex story, but nature makes extensive use of triangles and of hexagons. And you'll see this all over at many levels in the system. And look how these straight lines of energy, when these spherical shapes come together and form these triangles and hexagons, look how the spirals, how those spiraling curving lines are beginning to emerge. Now, why does nature use triangles and hexagons so often? It's because living things are and must be energy efficient. We cannot tolerate shear in our systems. They must be globally responsive in order to survive. They have to function as integrated whole organisms and have a cohesiveness that's independent of gravity. They have to be materially efficient, and they have to function as systems. Let's look again at Steve's unsolved problem and his quest. He had been trained in traditional biomechanics, which teach the body as if it were assembled from different parts, and assumes that you could calculate out forces within the body the way you could in a machine where you can measure what's going on outside of the body, something that happens independent of a body. So these machine models of the body were brought into biomechanics definitely in the last 360 years a lot, but really if you look at the spine as a column concept, that colorful spine of Osiris, that's from ancient Egypt. So nothing new here to model the body like the buildings and the machines that we make, and to imagine that that's what's going on inside of us. But really, when you think of it, people had no other choice. We had been building things this way for thousands of years, and it was the only way we knew how to build. But 100 years ago, or maybe a few years fewer than that, sometime in the last 100 years, something new was devised by humans, a new way to build. And this new way to build creates structures that have previously unseen and unimagined behaviors, relationships, movement patterns. The mathematics is new, and the mathematicians are still working on it. The force interactions are new, the force distribution patterns are new, and this new way of building became known as tensegrity. In a tensegrity, the cables, which are on the outside, manage only tension, which cables are good at doing. And the bars or struts, which are on the inside, manage only compression, which bars and struts are good at doing. And it becomes an interdependent system where all those forces and structures are in a win-win relationship. And the force relationships within the structure create a oneness so that the item is not gravity dependent. This particular tensegrity by Kenneth Snelson is called easy landing. And if you could take it off of its posts, you could turn it any way you want. It would not sag. Different from tensegrity, the structure, is tensegrity, the word. And tensegrity, the word, is, of course, not a structure. It's a Fullerism. It's a word invented by Buckminster Fuller, which combines two other words, tension and integrity. Integrity, of course, is not a building material. These cannot be made of integrity. But integrity is the quality that Fuller realized results in this particular tensocompressional configuration. Tensegrities exhibit really unusual qualities. They function as systems. There's non-linearity in their movement. They're auxetic. They expand and condense omnidirectionally. They're fully integrated structures and holistic. They behave as a one. There's a complexity to what happens with them that's related to all of that. There's also omnilocational force distribution in these systems. And so they're globally responsive. And they have emergent properties, which you've heard about from some of the other speakers today. They condense helically, they expand helically. There's a cohesiveness that's independent of gravity. They're materially efficient and they're energy efficient. So back to these unsolved problems, these quests of mine and of Steve's. What we really needed here was something called a decoder ring. Now, when I was a kid, you'd get a decoder ring, maybe in a box of Cracker Jacks or cereal, and if you had one, you could write a secret message, and someone else who had the same decoder ring could figure out what that secret message was. So what was the decoder ring that could solve our problems? Well, there was Steve, as we said, down at the Natural History Museum, spending weeks and weeks looking at these huge dinosaur bones, trying to figure out what was the nature of our structure. He was so frustrated one spring day that he went outside and he just sat on the bench and he thought he'd just think about it all for a while. When he looked to his right, he could see the Washington Monument, and he thought about how he had been taught in medical school to model a spine like a stack of blocks, which he knew didn't make any sense. He looked across the mall as he began to turn his head to the left, and he could see many of the construction cranes that were across the city's skyline, fully triangulated structures that are energy efficient, that distribute forces throughout. But there was something about their static structure that didn't quite work, although he was getting closer. And as he continued to look to the left, his eyes came upon the Hirshhorn Museum, a new museum that had just been opened in 1974. Steve, of course, went to see it soon after it opened. and he saw a sculpture on the grounds there. And something today, on this particular day, popped into his head. Maybe he needed to go back and look at that sculpture. That sculpture was by the artist Kenneth Snelson. It was a tensegrity tower called Needle Tower. And with that, Steve had essentially found his decoder ring. He got in touch with Snelson. He started to build tensegrities, learn everything he could about them. He started to put together his theory of biotensegrity. 33 years later, when I stumbled upon the concept of biotensegrity after reading Tom Meyer's anatomy trains and realizing that I did not understand this flat picture of a tensegrity structure that's inside the book, and I started to build my own, and I was shocked at the behavior, I started to hunt around, and I found Steve's website. And I realized that this was a system that could begin to perhaps solve the mystery of the Tai Chi classics for me. So I had found my decoder ring as well. All of these different things started lining up with what I was reading in Steve's papers. So down the rabbit hole I went, and that brings us to our next part of the presentation, biotensegrity and what it is and why it matters. We're going to talk about the distinctions between tensegrity and biotensegrity, and also between biotensegrity and the applications that people come up with when they have an understanding of biotensegrity, things that they use, whether it's medical invention or techniques or how to improve sports training. So here we go. Biotensegrity, what it is and why it matters, with apologies to my friend David Lasondak, whose book, which you should get, is called Fascia, What It Is and Why It Matters. Biotensegrity is essentially the study of tensegrity structures and principles in biology. So we have to know what biology is if we're going to study biotensegrity. And biology is an investigation of all living organisms through all time, their systems and subsystems. Biology is a systems science and is completely accepted these days as also a soft matter science. All the soft matter scientists will tell you that all living things are soft matter. Biology is not goal-oriented other than to just study and learn about biology. As Graham Scarr says, we're learning about biology as itself. We're not trying to do anything with it. And so tensegrity in biology, has all of these aspects to it because it's part of biology. And it's separate and distinct from the study of tensegrity. And it's separate and distinct from the study of how biotensegrity concepts or awareness or information can be applied. And biotensegrity has inspired and informed all kinds of things. Manual treatment protocols, such as Anna Crowell's pelvic therapies, and we have a whole biotensegrity party about that. June Kwak's tensegrity poetry, which is really fabulous to see. Christian Castro Arenas' biotensegrity informed design innovations, Randall Alley's prostheses, all biotensegrity inspired or biotensegrity informed. So just to clarify those distinctions once more, tensegrity started with art, and it's now a study also of architecture, engineering, mathematics. Biotensegrity is a part of biology that studies tensegrity as a concept applied to biology. And from both tensegrity and biotensegrity, people draw inspiration. They come up with new concepts, and informed by biotensegrity and tensegrity, or inspired by them, they come up with applications, inventions, innovations, all kinds of things. Now, none of these are biotensegrity itself, but they may be applied biotensegrity. So, finally, we get to the last section, biotensegrity as a systems view of the spiraling, fractal, functional structures and behaviors of living organisms. When we study biotensegrity, we build a lot of models. Eleftheri Pavlidis, who was on the biotensegrity party a week ago, gave me this wonderful word he's come up with, dactylnosis, learning through the fingers. And we do a lot of that, and there's a lot of that in my book, Everything Moves. That's why there are so many activities. You can learn this through your fingertips. We make tetrahedrons using toothpicks and raisins or marshmallows so that we can study stability and how things fall together. Using magnets or toothpicks or whatever, we build tetrahedrons out of tetrahedrons out of tetrahedrons. And we learn about nested self-similarity and fractality. And there are other emergent shapes within these. Too much to go into today. But from these minimal energy structures, following straight line force interactions, we discover through our fingertips that spirals naturally self-emerge. And if you grab a piece of paper and a pen or pencil, I'm going to show you a little bit about that right now. We're going to draw a Fibonacci spiral. You just start by drawing a square, and we'll call it a 1 by 1 square, and it doesn't matter whether it's an inch or a centimeter. You draw a square next to it of equal size. So now you've got two 1 by 1 squares, and together they're length 2. The next step is, now that you've got this rectangle, you're going to build a square on top of it. And it's going to be a 2-unit square, effectively. And now you've got a 2 by 2 square on top of two 1 by 1 squares. And the long side of this new rectangle is length 3. Everybody with me? Let's keep going. Now you have now drawn a golden rectangle. And we're going to draw a series of these. We're going to keep this pattern going. You're going to draw a 3 by 3 square on the long side of that rectangle. And that creates a new, larger rectangle. So each time we build a new square, we get a new rectangle. And it has a new longest side of a new length. And this corresponds to the Fibonacci sequence that was devised by a guy named Fibonacci who lived in that town of Pisa where we saw the Leaning Tower earlier. And you just add the previous two numbers together to get the third. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. And so you can actually build something this way. And each new rectangle generates a new square. Once you've run out of space on your paper, you can build your spiral. So let's look at what we have here. This spiral here is like that spiral there, is like that spiral there. There's a nested fractality to the system. They're made with golden rectangles. It's called a Fibonacci spiral. It has self-similarity and fractality. So that's just a little taste of what we study. Fibonacci spirals are ubiquitous in nature. And Fibonacci fractals and fractal Fibonacci spirals are also ubiquitous in nature. And so you can begin to see how the spirals in nature, and here's a wonderful David Goodsell painting that shows part of a sarcomere, actin filaments in blue, myosin in red, the long yellow proteins are the protein titin. Look at all of those spirals. Functional structure, biologically, you'll see spirals showing up everywhere, but not just in biology. This is just how things come together. This is, I believe, the South Pole of Jupiter. Might be the North Pole. This is from NASA. It's called the Rows of Galaxies. Spirals are everywhere. And take a look at the spirals in the skin of this sweet little baby snake. And for that matter, the spiraling pattern of my hand. What living things need is functional structure. And functional structure is not arbitrary. Thank you so much. This has been a systems view of biology, biotensegrity, and its fractals and spirals. I want to thank my partners of the day, Chris Marita Clancy, Mariana Barreto, Kayla June, Diane Woodruff, and MJ Porter. We all coordinated very carefully together so that you'd get a comprehensive presentation. And we want to thank Anna Outsubo for giving us this opportunity to present to you today. Please donate to the Biotensegrity Archive if you enjoy my work. Thanks so much.